Okay, so now we continue with Simon Pekar talking about Carrollian derivations of a BMS flux balance law.
Thanks, Andrea, and thanks to all the organizers for putting up this very nice workshop and giving me the opportunity to speak. Yes, so I would like to talk about this work, no pointer, with Adrian Fiorucci, Marius Petropoulos, and Mathieu Villat that came out recently. And in this work, we asked the following question, which is, oh, I think there is no battery. Now it's working. Okay, very good. So the question that we asked is it possible to reproduce the BMS flux balance laws on the mass and angular momentum aspect, starting from purely boundary considerations? So I want to, and the answer that we want to try to convey is that if we are able to set up a variational principle at Scry, can we derive from them the BMS flux balance law? So as you can see, it's pretty similar in spirit to what Yellow was presented, although I will not make a lot of references to the bulk. I will work mostly purely intrinsic to the boundary. And well, to answer this question, there are a couple of facts that we have to address. The first of those is that these are not conservation equations. So this is what is making it difficult in comparison to ADS. And so what we are naturally led to analyze is the fact that the flat space analog of a holographic stress tensor is not enough in order to answer this question. As said already by Jelle, Ashtekar's insight was that the radiation under the form of the asymptotic shear actually lies in the connection when you work in the conformal compactification setup. And so what we would like to propose is a variational principle that includes both the metric and the connection. And the response to these variations are what are usually called momenta and hypermomenta in metric affine gravity language. And this set of momenta is going to form our holographic dictionary. Very good. So
I've been saying this here and I'm confused. What does it mean?
Yeah. So indeed, I'm not going to present any candidate holographic dual to gravity yet in this talk. But the point is that if we have such a dual in our hands and we perform the minimal coupling to the geometry, we are going to derive some data. And these data are going to obey some evolution equations, which is basically the generalization of the conservation equation for the stress tensor, but in the presence of a non-trivial connection which possesses ambiguities. So what I'm going to argue in this talk is that if we had such holographic action and we compute the stress and the hyperstress associated to this action, then these have to follow some prescription that I'm going to present in the end in order to reproduce the Bondi evolution equations.
So you'll postulate some things, some properties you should satisfy.
Yeah.
Oh, okay.
At some point, I will postulate that I have an action, and then I will work with the variation of this action. Yeah. Okay, so if there are no further questions, this is the plan. So I'm going to quickly review what we expect coming from ADS and why it doesn't work naively in flat spacetimes. Then I'm going to spend some time describing the most general boundary geometry at Scry, and this is going to overlap just a bit with Adrian's talk. And then as an important application, what we're going to do is to derive these flux balance laws. So let's get started. Yeah, I'm not going to spend a ton of time on this because it has been already mentioned by Jelle. But if you work in ADS4, asymptotically locally ADS4 in the Pfefferman-Graham gauge, and you introduce this conformal compactification of Penrose, what you realize is that the relevant data in order to reproduce Einstein's equation are the boundary geometry that is encoded in G and the holographic stress tensor T, which sits at the third order in the expansion. And once you apply the holographic renormalization procedure, your the variation of the Einstein-Hilbert renormalized action reduces to this boundary term where the holographic stress tensor is the response to the variation under the boundary geometry. Of course, this variational principle allows you to recover Einstein's equation very simply by evaluating it on a boundary DFO and boundary Weyl transformation. So if you insert this in this variation, you get immediately that the stress tensor T mu nu is conserved and traceless. Of course, as we all know, asymptotically flat spacetimes are rather different. And okay, the first and maybe least scary difference for this audience is the fact that the boundary geometry is non-Lorentzian. But by now we are used to work with Carrollian geometries. And correspondingly, the symmetry group at the null infinity is infinite dimensional. The second fact is what I was advertising before, which is that Einstein's equations are not conservation laws. And correspondingly, the charges that you build upon these two quantities are non-conserved and non-integrable. Okay, this is also one comment related to the fact that you have a symplectic potential in your phase space, which tells you that the action, no matter what regularization or renormalization scheme you apply to it, is never going to be stationary unless some form of no radiation condition is imposed in your space-time. So, yeah.
I think there's one point that sometimes there's confusion about is that, well, if you talk about variations of fields on something that is more like a Cauchy surface, then there's, it's natural that this thing arises, and that, so the simplest example is just point particle. There's no space. Okay, you do the variation of the action, you get a boundary term which is at time equal t equal 0 or something like that, and it's of the form q dot delta q, right? But you're not going to impose that q dot is 0. It's just,
of course not. I'm just trying to make parallels with ADS.
Yeah, but I think, the Ashtekar-Strobel symplectic form, where you have the same thing happening, where you have NAB delta CAB, is the analog of this q dot delta q in.
Yeah, I agree with that.
For the point particle. So there is no reason to impose that the news would be 0, because it's not a boundary at spatial infinity. It's more of a Cauchy surface.
Oh, I agree with that. Yeah.
Okay. No, it's just that because it says that, okay, action is not stationary unless we impose that there is no radiation. But okay, there is no reason that we would want to do that.
Well, this is an observation.
Okay. No, it's okay. It's just to be clear about that point.
So yeah, so the picture that I have here is also to illustrate the fact that usually we are treating scry as having a definite Carrollian metric and vector field, and then the conservation laws that we would have for M and A, the mass and angular momentum aspect, is going to be perturbed by the presence of sources coming from the bulk under this CAB. But what I'm going to advocate is that this is not a correct view, and in fact we have to consider the shear as part of your boundary geometry. And when you consider this, you are naturally led to introduce some momenta for this part of the boundary geometry, which sits in the connection. And
so
yeah,
just which action was not stationary? The bulk action is not stationary.
Yeah.
If the radiation doesn't vanish.
If
the Einstein 4D action is not stationary if the radiation doesn't vanish.
Well, if you have some non-zero NAB, you cannot make this variation 0. This is just what I'm saying.
Oh, there are solutions with news. So you're saying that they just
No. So what I'm saying is that if we want to reproduce this sort of renormalized variational principle in flat space, there is going to be a piece which is the variation of the shear times the news.
Yeah.
And this in general you cannot cancel unless you impose that the news somehow vanishes.
It doesn't get cancelled by some corner term people add or something else.
No.
Oh.
Okay.
But if the
by a corner term
or a given Hawking.
Things that you don't have flux at infinity. Because as soon as you have flux at infinity, you will have the pull back of the symplectic potential, which is not vanishing. was also the one by the surpass at 99%.
I see. Okay. Maybe I'll ask again.
Okay, so any questions regarding this introduction? Okay, so if not, I'm going to first talk about geometry, and the starting point of this is always this BMS ansatz that we have all seen. And I'm going to jump directly to the conformal compactification, where we take the conformal factor to be 1/r. And when you do this and pull back to scry, you realize that your boundary geometry is Carrollian. As Jelle mentioned, the 2D metric here is not completely free because its time derivative, the trace-free part of its time derivative must be set to 0. This is one of Einstein's equation. Usually we take it to be completely time independent, but Glenn had a very nice talk where you can use this conformal factor to do some interesting physics. Then the connection at scry is given in the purely angular part by the Lebesgue-Vita connection of gamma. And crucially, there is this gamma UAB, which encodes the shear. Now, what we want to do is to make everything completely covariant. So from now on, I'm only going to focus on the boundary geometry with no reference to the bulk. For reasons that I don't have to explain, but you can find them in the talks of Adrien and Marius, we are going to use a carton frame. It's going to be much easier to work with that. And what we're going to do is to decompose this basis of one forms into the clock form, which is the one evolving along the null direction, and then a Zweibein for the sphere metric. Okay, as soon as you are working with a carton frame, you're going to have some ambiguities in the way that this is defined, and this is encoded in local transformations of the frame. So you have local rotations acting on the Zweibein, local Carrel boosts acting on the clock form. And because we're not working with one particular representative of a metric at infinity, but a conformal class of them, you also have local Weil transformations acting infinitesimally in this way. Of course, you can go back to the metric formalism by taking the square of this Zweibein. So once we have our local frame, which we parameterize in this way, we can ask the question of how to build a connection on this space-time. And we're going to start from the most general connection and then impose some constraint in order to reduce it to something that we like. The first constraint that we're going to impose is that it is torsion-free. This is a very natural requirement, which we can think of, for instance, by considering that this should be the pullback of a bulk connection, which is naturally torsion-free. This is going to impose some constraints on these coefficients. We are also going to impose that it has some form of metric compatibility, but metric compatibility alone is not a Weil invariant statement. So to make it Weil covariant, we have to introduce this extra one form, which is a Weil connection, as it transforms inhomogeneously under Weil transformations. And this is what we're going to consider. We can also build this Weil covariant derivative curly D, which takes into account the Weil weight of our objects. For instance, here you can see that the Carrollian metric has Weil weight -2, and the Carrollian vector field has Weil weight 1. So with this Weil covariant derivative, equations are going to be very easy to write because they're just going to be, for instance, curly D acting on this upsilon is 0 and on G is 0 as well. Okay, so yeah. We have one question.
Yes, so here you're allowing the boundary metric to depend on time?
Yeah, I'm doing the most general thing
Okay,
that is allowed. So yeah, as Simone anticipated, this construction only works if the geometric shear of the manifold vanishes. So this is the frame analog of this condition that I wrote here. But generally, we will work with a non-zero trace, non-zero expansion. Okay, when you do this, you realize that all of the connection is not completely fixed. There is an ambiguous part. And well, here you can think of this equation as just me giving a convenient expression of this omega 0 ij in terms of a tensor that we like, but I'm not making any reference to the bulk yet. You can actually prove that if you consider a connection in the bulk and you pull it back to the boundary, this tensor is going to be populated by the asymptotic shear, but here we're not going to make any reference to the bulk. Okay, so now I have constructed for you the most general boundary geometry and connections at Scri+. Of course, it's the local symmetries that act on this is huge. It's the most general set of transformations that you can have. It's going to be very convenient to make a choice of frame that is going to reduce the BMS frame. So I'm making this particular, now in this slide, I'm making this particular choice that tau is the exterior derivative of u, and that theta is parameterized in this u-independent way. And the picture is as follows. You start with your reference Bondi triad, and you apply a diffeomorphism. This is going to bring you out of this gauge choice in general, something which I denote by tau prime and theta prime. But you can use local symmetries to bring you back to the original frame. Of course, this can only work if two things are satisfied. The first is that the local transformation parameters are fixed in terms of the diffeomorphism. And the second is that this psi is actually an isometry, a conformal isometry of your frame. So this is what I'm doing in full details here. So if we require this equation to hold, what we find is that all of these local Carroll boost, rotation, and Weil transformations are fixed in terms of the components of the diffeomorphism. And this diffeomorphism must satisfy the following constraint, which tells you that this is basically a Carrollian, a conformal Killing equation for Y. So all in all, Xi is a BMS4 vector field. The nice thing about this total variation operator that I constructed here is that when you act on the solutions, on your connection with it, it actually reproduces the BMS transformation of the shear. Why? Because as I was arguing before, this Cij is a part of the Carroll boost connection of your manifold. And we know that the Carroll boost connection transforms inhomogeneously under Carroll boost. That's its property. But the Carroll boost parameter is fixed to be the gradient of this f function. So when you plug this transformation here, you find that the shear, what I call the shear, now transforms correctly with two derivatives of the diffeomorphism. Okay, one last thing before I move on to the meat, which is the boundary variational principle, is the fact that since our boundary geometry is no longer Lorentzian, that it's Carrollian, the Riemann tensor of your manifold is no longer pure trace, right? As in 3D, you would expect that the Weil part of the Riemann vanishes, but this is actually not true. So you can compute some components, and I computed these two ones because they are going to be relevant. This one is what I call Nij hat, which is a sort of physical news, because you can compute it to be the difference between this tensor Nij, which is just the u derivative of the shear, and this Nij alpha, which is built upon the Weil connection in this way. So this, okay, let me pause here for a moment because this expression was derived in many works, including Compare and collaborators, but also Campiglia and Perazza using a conformal connection. And its transformation properties under BMS is such that it compensates precisely the inhomogeneous part that comes from the news. And so for this reason, it was called the vacuum news, and it is related to the Guéroche tensor by a trace. So yeah, all in all, this R0I0J component of the Riemann tensor transforms completely covariantly under BMS, as it should because it is a Riemann curvature. Yes.
So this construction, as far as I know, Q is time independent. Now,
Yeah.
when Q is time dependent, do you still have the property that this curly Riemann is conformal invariant?
Yeah.
Because I would have thought that you need more pieces now to subtract because now you can do conformal transformations that are time dependent as well.
Oh,
And
you
I
mean,
think that
so
won't
you
work.
want to extend your symmetries to include time-dependent Weil rescalings?
No, I mean that is not a physical object because now in your theory, you're allowing conformal transformations that are time dependent. So you have to make sure that your quantities are conformal invariant under this more general
Yeah,
and not just
yeah.
the, so I think,
Yeah, they will be. Here I
so
took,
there will be more terms, or you will
there
check
will
that
be
this
more
is
terms.
invariant under, oh, I see.
yeah.
So before calling it physical, we should wait then.
Sorry?
Before calling it the physical one, we should wait until you show us the extra terms, right? No. Yeah, but my question was, under time-dependent Weyl transformations, that was my question. Okay, good.
Each case, variant of the superoperation, the superoperation generates a variant transformation, which is DAYK.
Yeah, but the first answer satisfies me. So you say it's invariant under time-dependent conformal transformations.
Yeah.
That's the key point.
Yeah. And in general, if I move out of this gauge, there would be more terms inside this curvature. Okay, you also have this 0 ijk part of the Riemann tensor, which is the curl of the shear. I think Dave Nichols called it the magnetic shear. I find it interesting because here you have like electric and magnetic parts. Okay, you also have that the purely spatial part of your Riemann is pure trace, and it's giving you the Weyl covariant Ricci curvature of your 2D manifold. Okay, any questions? Yeah.
It's probably unimportant, but that just plain du is probably not super translation invariant. So do you need a connection piece in tau?
Just taking this tau to be du?
Yeah, that's not invariant, and it's u going to u plus f of cc power. So
No, but that's fine. I mean,
it's just choice. Okay, I guess.
Tau is not something that you see on the boundary, right? The only thing that you see is the Carrollian metric and vector fields, and these are invariant. Tau is not going to be invariant under a super translation, but under this compensated transformation where you combine a super translation and a Carroll boost, it is invariant.
Okay.
In fact, this object here plays the role of the action of a diffeomorphism from the point of view of the bulk.
Okay.
Okay, so if there are no more questions, let me jump in. So this is what we were discussing before. So now I want to backtrack a little bit and imagine that I have a Carroll conformal invariant 3D field theory that depends on some set of fields. And what I want to do is to extract some, let's say, holographic information from it by performing the minimal coupling to the geometry. And crucially, it's going to be a coupling to both the metric and the connection. So this is what I'm doing here. I just take now the variation. There is going to be one piece which represents the equations of motion for phi, and then the response to the variation of the geometry. So these two vectors here, TA and omega AB, are called the momenta and hypermomenta. They're going to be in general functionals of the on-shell value of the fields. And now what I do is to go on-shell for these matter fields. So I'm completely agnostic about the matter content of my theory. I'm going to work purely with this delta SB, and I put a slash here because in general, it's not going to be a total variation once I go on-shell for the fields. One comment, I'm not sure that I have the time to make it, but it would be really great if we could match this delta SB with some other procedure that Yellow talked about, or Marika, coming from a bulk holographic renormalization. So now I'm going to work purely with SB, this geometric action. Well, geometric in the sense that it only involves the geometry. And I'm going to ask that it is invariant under all the possible symmetries that I have in my problem, namely Carroll boost, rotation, Weyl, and diffeomorphism invariance. So, okay, this is the constraint that you get. As you can notice, this T0I, well, all these right-hand sides are not zero, and this is due to the fact that we have introduced hypermomenta in the game. There is absolutely no symmetry breaking in this procedure. These terms are very well understood from the point of view of metric affine gravity. So, for instance, the fact that T0I is non-zero, but is equal to this right-hand side, is not a sign of Carroll boost symmetry breaking. It's just the fact that you have some hypermomentum. And in fact, I think you can even trace this back to Newman and Penrose. The fact that T0i is not 0 is due to the presence of radiation, because well, in this paper of Laurent, it's something that is equal to the divergence or the covariant divergence of the news. So because we have some ambiguity in our connection under the form of the asymptotic shear, the hypermomentum associated to this quantity is going to be the piece responsible for driving the non-conservation of T00 and Ti0, which I'm going to show you in a minute how it's related to the Bondi mass and angular momentum aspect. So yeah, in general, this invariance under diffeomorphism equation is going to take this form, where the right-hand side is sourced by purely geometric terms composed of the Riemann and the hypermomentum. So, okay, now I'm writing this evolution equation in its full glory and in the Bondi gauge, where you can see that, for instance, the U derivative of T00 has some what I will call soft terms, because they depend linearly on the hypermomenta, and this hard term, which is the product of a Riemann part and the hypermomentum. And similarly for the angular momentum aspect. And now what we do is we take this expression, we open Barnish and Troussard, and we match. So what we did in the paper is to say that if we take T00 to be equal to 4m, Ti0 is equal to twice the angular momentum aspect plus some corrections, and all of this choice of hypermomenta, what we reproduce here is a Weyl covariantizations of the BMS flux balance laws. Of course, when you go to the frame where this Weyl connection alpha I is equal to 0, these reduce to the usual BMS momenta, so the objects that appear in the metric. Céline?
Just maybe you said it. Do you have a comment why the soft sector is in the T's and the hard only in the hypermomenta? Like why? Because it's the red is the one that is going to source the fact that the stress tensor is not like on your previous slide. It was really the omega that this one that was really the omega. No, so can you comment on where is what? Sorry, I was getting a bit lost. So
okay, so the really the hard part of the radiation, we understand it geometrically as coming from the fact that you have a piece in your connection which is not determined by boundary geometry, and so the response to this variation is going to be what we call the hard part.
Okay, but it's kind of surprising that, do you have a comment why the soft sector is going in the T's in the next slide and why the hard is going into the omegas?
Okay, so actually I had a hard time coloring this slide because this distinction is not so clear.
Okay.
In fact. So there are some terms that are definitely hard, which are quadratic, let's say in the news. But this decomposition is something that, it's simple enough and it works. But because your variational principle is a bit redundant in the fact that you vary with respect to the geometry and the connection, you can move around certain pieces and still satisfy these equations.
These evolution equations are the equations of motion of your Carrollian theory?
Well, you can, no. The equations of motion of the Carrollian theory are, with this we imposed it, we went on shell already for the matter fields. These equations, they are conservation, I don't want to call them conservations because they're not, but they are the analog of the conservation of the energy momentum tensor of the theory.
They're not imposed through a variation of any field of your action of the.
So the fields of this action, they are here. We went on shell and we worked on shell for the matter fields.
And these evolution equations are some constraints you've imposed.
They follow from diffeomorphism invariance of your boundary theory.
I see. So this is the intrinsically a boundary constraint.
Absolutely. Absolutely.
It's boundary. But you don't want diffeomorphism invariance in the holographic dual.
Sorry, what? You don't?
It's supposed to be the Carrollian dual to some bulk theory. Oh, hello?
Yeah.
Yeah. I wouldn't have expected you to gauge diffeomorphisms in the boundary layer.
We're not gauging them. We are just requiring that when we couple our Carrollian action to a general geometry, the theory that you have is diffeomorphism invariant. This is the same statement as when you start, let's say, with this sort of action. Let's take a silly example. I take this action to live on a 3D Lorentzian manifold. I want to compute the stress tensor of this theory. What I will do usually is to couple it to a general Lorentzian background. And then this is the Einstein-Hilbert stress tensor, vary with respect to the geometry, derive the T mu nu, and then its conservation follows from diffeomorphism invariance.
You're saying you're not going to gauge that?
No. Another one? Yeah.
Yeah, in the next slide, when you match it, no, I mean, when you're
That's fine.
matching it, yes. Do you have any understanding of why?
I didn't hear, sorry.
Is there a reason why they should appear in this precise combination, or it's just you look at them and match?
Very good. So this is the only step of our derivation where we are, making reference to a bulk and the fact that we have Einstein gravity in the bulk, and therefore the dictionary that we get is this one. For the moment, we are not able to derive these expressions, let's say, from first principle. Yeah, going to conclude. But that's something that we're working on. So since I'm out of time, I'm just flashing here that this boundary variational principle is able to reproduce the Wald-Zupas symplectic potential and the charges that were computed by Glenn and Cedric in using covariant phase space methods. Although here we can be as general as we want because we are working with the most general boundary geometry. So yeah, to conclude, this was an intrinsic derivation to the boundary of the BMS flux balance laws, where we have used the geometric setup implementing all the local possible boundary transformations. It gives a geometric origin of BMS fluxes that I'm not claiming is completely new. I think many people have understood before that since the radiation sits in the connection, the response to the radiation has to be thought of as some form of hypermomentum. But nevertheless, this set of momentum and hypermomentum should constitute a first entry in the flat holographic dictionary. What we want to do next is to go even more general, and in particular to include superrotations. The link with ADS written in a Bondi gauge would also be interesting to do, as was explained by Marius. We can obtain the Bondi equations by a flat limit coming from ADS. Related to Susheta's question, we want to prescribe the form of hypermomentum in a bit of a more agnostic way without making reference to a bulk. And finally, work a bit more on what is this S of phi theory and what does all of this give us, tell us about the Carrollian holography altogether. So with that, I want to thank you.
We're running a bit out of time, but are there maybe last urgent question? Okay, there have been a lot of questions during the talk, so let's thank Simone again then, and we can discuss during the topic.